Hey, hi people, how's it going? It's been a while since I released a video about data structures and algorithms, and Compiler's channel is basically talking and trying to explore for ourselves um, what the foundations and fundamentals of computer science and its applications in areas that include geospatial sciences and engineering and and other informatics fields as well. All right. So, um, thank you very much for taking time to join us and listen to us today. And of course, taking time to subscribe to um, this channel as well. All right. So, as you can see, today we have something exciting for us to go through. We are going to see how to implement a binary search algorithm, right? What's a binary search algorithm, and what did we do the last time? In the last lesson, we took a look at the linear search, right, where we talked about the fact that this is a search procedure where the algorithm takes to go through or walk through the array block by block or the list step by step, one element after the time. It makes a comparison with the target element, right? So, if the target element is found, um, the operation seizes and returns the index of the element, whereby the index, wherein the index defines the position of the element in the array memory space. Okay, we talked about the fact that the complexity of it was quite costly because you would sort of have to move through each element. We sort of have to. We can take a look here. Linear search, um, Wikipedia. Alright, so you sort of have to move through each element one after the other, and that results in the time complexity of O of n, right? So it's linear. You move through each of them, you leave no stone unturned. You check and see, then you know that's how some way somehow humans we are, right? But today we want to move on with the search algorithm and try and learn something new. This is binary search, as the name suggests, binary, right? What are we searching? What was binary about this? Okay, so as we saw in the last time, linear search, also known as a sequential search, it has a worst case performance. So most of the time, we care about the worst case performance of n, right? In the best case, it's a constant time case where the 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 search target element is almost equal to the index of the first element. You know, right? Or the element in the array, the first element in the array, and put that way, index of 0 or 1, depending on the program language you're using. Okay, so today we would just take a look at binary search, try and implement it. Of course, you know, this is we read and we do. Okay, nothing. We just try and see how we can map up, gather information on the internet, and see how we can put them into practice. Right. So let's dive straight into it. Okay. So a binary search is also known as a half interval search, right? Logarithmic search or binary chop. So it's an algorithm. The search algorithm finds the position of a target value within a sorted array. I would like us to take note of this: a sorted array, right? So in a case where the array is unsorted, binary search might not be a good algorithm in searching for target values or target elements. So the binary search compares the target value to the middle element of the array. Okay, so at the first instance, at the first iteration, it does compare the target value or the target, elements, the elements under search to the middle value in the array. Okay, then what else? It says if they are not equal, the half in which the target cannot lie is eliminated, and the search continues on the remaining half. Okay. Again, taking the middle elements to compare to the target value and repeating this until the target value is found. Right. So if the search ends with the remaining half being empty, the target is not in the array. Okay. I hope it's a bit clear. So basically, well, sometimes Wikipedia can be a bit um, bulky in terms of understanding, but basically, what the text is trying to tell us is that um, at each iteration, or at each time where we look at the loop, the search space, which in this case we can see, let's take this element for example. The search space is divided into two, and the middle element in the search space is compared to the target, the value on the target, the value in search, I'm sorry, right? And if they are equal, it returns the algorithm returns the index of that element, and um, that's it. The procedure terminates. But if not, it moves some pointers that define the search space, um, you know, to a different points in the array, and that's sort of like gives it a halving process, right? It might be a bit tedious to understand by just like talking. So without wasting much time, sorry, we would just dive straight into the code and see how it works step by step, right? But before we do, let's take a look at the worst case performance. This is log n. What it means is that um, since we will be dividing the search space by two or by half, you know, we'll be halving the search space each time. Um, it's in this worst case performance. It gives you a logarithmic um, index, or a logarithmic performance, right? Where it's you unlike the linear search where um, the performance is an order of n. This is an order of n divided by two, and in mathematical terms, a log is the best way to represent this performance metric, right? So we'll just jump straight into the code and see how best we can get ourselves ahead of this game, right? So we would start by creating a class for this. Well, although we can go the functional programming paradigm approach, I'd prefer we just go ahead with this. So we create a class, and we come up with a constructor. Okay, and this constructor is going to so upon the creation of the class, we want to pick an array, right? You know, the user can input an array, and an instance variable of the array will be created. Okay, so now we can define some methods on the class, and the first one would be to find. Of course, the find operation is what we are interested in, and it's mainly what the binary search does, right? So we are going to find a value, okay, a value or a key. We can, we can call it a key, a value, or whatever, a target element. Well, for the sake of sanity, let me just name it as a target element. Okay, so we are searching for a target element, and basically we want to return the boolean status of the elements in the array. Okay, that's good. So what do we do from here? As we read it in the Wikipedia page, um, it's ideal for us to define the the boundaries, right? The bounds of the search space, right? And in an array, the only metric, one of the best metrics we could use is the 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 starts of the array and the end of the array. Okay, so how do we define the start of the array, right? So we can say the start of the array is the lowest point of the array in terms of index wise. So we can say, okay, so the lowest index, okay, lowest index or the start of the array is actually, let's say, 0. Okay, then we have the high index, which is the upper bound or of the array. Well, I would like to change the names. I don't like no index. Use lower bound, lower bound, lower array, lower bound. Okay, okay. Let's give it 0, and the upper. Oh, sorry. Upper bound is mostly equal to the length of the array minus 1, because we are starting from 0, right? We are not starting from 1. In the case where the first index of the array is 1, we could, simply just, start from 1, and the upper bound will be equal to the length of this array that will pass in there, right? So we can get the array, and yeah, of course, in Python, think we can define the length. We can find the length of the array using the inbuilt length function, right? The length function. This should work. Yeah, and from here now we are going to see that while the lower bound, is less than the upper bound, okay, we are going to define the middle bound. Actually, the middle bound is also the index position of the most middle elements in the array, right? I'm calling it a bound, but it doesn't necessarily sound right. It should be the middle index, right? So if I change this to be the middle index, then I'll have to sort of change these ones to be the because we should have lower index, upper index. We should have sanity in naming. Okay, so we know what we are doing. All right. Great. I'm sorry. All right. So how do we calculate the middle index? Okay, given an array. So it's actually the length of the array divided by 2. But we can go with this route instead, since our lower index is 0. So we can start from the lower index, and we see plus the difference between the high index, okay, it's the upper index, sorry, the upper index minus the lower index, divided by 2, a floor division divided by 2, right? So we get whatever difference is in here divided by 2, but of course we return only the whole number, the nearest whole number division, a floor division here, and we add it to this index. This is a good way, instead of just picking the upper index minus the lower index divided by 2. This works well. All right, so now what do we do? So we can see that this is the middle index, right? We can see that we can once we have the index, we can find the elements at that position, right? So we can see if our target element is equal to the elements at the middle index, right? So we're actually doing an indexing operation here. Want to find the element at the middle index, then we can simply return the middle index. Okay, well, if it happens that the element we are looking for is greater, right, than the element at the middle index, right? So we can see else if the target element we are looking for is greater than the elements in the middle, then we can see the middle index, then we can see the our lower bound, right? So we take the lower index here and shift it all the way to the middle index plus 1, right? Else we see that the higher index, or the upper index, sorry, I keep on saying index, I think it should be 1 upper. Yeah, so the upper index should be equal to the middle index minus 1. So what we're actually seeing here is that if the target element, right, so if it's greater than the middle index, mind you, this is a sorted array, okay. I should be able to rename. Okay, I should be able to rename. Yeah. So I'll rather call it a sorted array instead. Okay. So the sorted array. Let's call this the sorted array. Alright, so now if the target element we are looking for, it's not in the lower half of the search space, that then we move the index to the lower index to just the middle index plus 1. So ahead of the middle index, we now move the 0 position initially to the middle index plus 1, thereby cutting off the lower index. So this time around, at the next iteration, the procedure wouldn't have to look through the index from 0 to the index of the middle minus 1, or the index of the middle. No, it will just like discard that and move on with the search space, the active search space, because that's where our target element might possibly be, right? Then if not, then we move the upper index rather to the middle index minus 1. Then we have found that as well. So in this case, then we are saying that the target element is actually less than the index of the middle one limit. Please don't be confused. It's actually simple. It's fun, and yeah, it's way easier than any one of you expects here. So if all these operations do not suffice, then we should return none, unfortunately, which this is a non-object, so we should return none and see nothing. The element you are searching for actually is not in the sorted array. So yeah, this will be it. Well, we can go ahead and test our functions, but I'm trying to think of any other method we can implement in addition to it. But since this is a binary search algorithm, these the find method, or the search method, is the most important thing. All right, so we can create we can test our procedure here, and let's see how that's go. Let's create a dummy function, name it main, and try and simulate that with the normal main entry points in other programming languages. Right, so we can create a binary search instance or objects from the binary search class. Then what do we have to provide? We can provide an array in here, but let's say array is given as 1 2 3 4 5, right? So we can pass our array in here. Oops. Okay. All right. So now we have our binary search objects active. Now what else can we do? Let's find let's say 2. Right, let's say find2, and that's the name of the variable. So binary is find, and we can pass in 2. Okay, so um, print let's output find2 here. Okay, so if our algorithm works, we should be expecting uh, the index of 2. In this case, the index of 2 is 101, right? So we should be expecting uh, expect 1, right? So we can go ahead in here and just create a namespace. Right, it's equal to a main namespace. What do we do? Let's just run this one here. Okay, so let's run our program in the terminal and see what we've got for ourselves. Right. Okay, so we have 1. Don't know if you can see in here, but yes, that's exactly what we're expecting. Our terminal is showing us 1. Yep, you check here, you see that we have 1 here. We can try and find another. So we can find, let's say, 6, and so let's find 6, and with the same approach, keeping 6 here, then print find 6, print find 6, find 6. Alright, so with this too, we should be expecting 5. Yeah, we should be expecting 5. Alright, okay. Let's go ahead and run our program in terminal and see what we have. Yeah, hooray, we have 5. Now for the last one, let's try and search for an element that it's not in. It doesn't exist, right? So not exist, find not exist element, and again let's just pass an arbitrary value, let's say 100. We know clearly 100 is not in our array in here, so we should be expecting none, right? So let's output this in console and see if find not exist. Expects 100, right? Expects none, I'm sorry. Yeah, so once we save this, let's run it, and hooray, our algorithm works as we expected it to. So this is 1, 5, and none. Alright, so this is the beauty of the binary search algorithm. Basically, the magic here is to divide the search space into 2 until the target element is found, right? Yeah, and as we saw in our Wikipedia documentation, in the worst case, and even in its average in its average case performance, you have the complexity to be an order of log n, right? Basically telling you that unlike the linear search, this divides the time or the space complexity by 2, right? And logarithm of n, and at its best case, where you have the elements sitting right at the start of the array, it's a constant time. It's just or where you have the element sitting in the middle of the array. I'm sorry, not at the right of the array. I'm very sorry. Where you have the element sitting in the middle of the array, it just like picks it up, right? Like picks it up one at a time, and it doesn't have to continue to divide the search space anymore. So, gang, thank you all for spending this 24 minutes with me. I think it was exciting. I also enjoyed implementing this along with you. And yeah, for sure, as usual, I'll push this to the organization. And if you want to take time and look at it again, this is a binary search for you. I promise I'll be consistent this time around, and we are going to implement higher order data structures and algorithms. Right. So thank you very much for staying along with me, and I hope you have a wonderful day. See you next time. Bye.